Okay, let's continue with our notes for 9.7b Lagrange error bound, and we're going to start with example 3. Write the fourth degree Maclaurin polynomial for f of x equals e to the x. Then use your polynomial to approximate e and find the Lagrange error bound for the maximum error when the absolute value of x is less than or equal to 1. Let's see, we should have memorized the Maclaurin polynomial series for e to the x, and that being 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial. We could continue, but we don't because we're dealing with a fourth degree Maclaurin polynomial, so we're going to stop at the exponent of 4. Now we're going to approximate e when the absolute value of x is less than or equal to 1, so safe upper bound is 1. We're going to replace all the x values with 1 to find the approximation using this polynomial. So all the x's gets replaced with 1, so we get 1 plus 1 plus 1 half plus 1 6. 6 comes from the 3 factorial, and the 24 comes from the 4 factorial. We add those together, we get 65 over 24. Now we want to evaluate the remainder for this polynomial. So the fourth degree polynomial remainder would be r of 4 evaluated at 1. So our n value is 4 because we're dealing with the fourth degree polynomial. And so all of our n plus 1s will turn into 5s. Z we're going to leave alone for now. The x value is the 1. And the c value is going to be 0 because we're dealing with a Maclaurin series, so we know the center is always 0. So now we have 5 factorial, we have 1 minus 0 to the 5th, and now this is asking for what is the maximum value for the 5th derivative of the function, and what is the maximum value that it can take on. So we know that e to the x is derivative as itself. So if we find the 5th derivative of e to the x, it will remain as e to the x. And e to the first power is 2.718. But just so that we can choose a nice number that's a safe upper bound, we're going to choose 3 as the closest x value. We know it's going to be much less than 3, but we know 3 is going to be a nice safe value that we can choose. So 3 will represent the highest, the absolute max that this can be, even though we know has to be less than 3, because we know e to the first power is somewhere in that range of 2.72. So we replace this with 3. We keep the 5 factorial. 1 minus 0 to the 5th is still 1. So 3 over 5 factorial is 1 over 40, which is 0.025. Now we know the approximation with the fourth degree polynomial is 65 over 24. We know the error is 0.025. So therefore we know that our upper and lower bound must be, give or take, this 0.025 off of this approximation. So 65 over 24 minus 0.025, or and that's the lower bound. The upper bound will have to be the approximation plus the error. So when we do that, we know our e value must sit between 65 over 24 minus 0.025 as a lower bound, and the upper bound being 65 over 24 plus 0.025. I know we're not supposed to use the calculator, but if we were to plug this in, we're going to see the lower bound being 2.68, upper bound being 2.73, and we know our e value, 2.718, has to sit safely between the lower and upper bound. Okay, example 4. Our function f has derivatives of all orders, so we're dealing with infinitely many terms for all real numbers x. Assume that f of 2 is 6, the derivative evaluated at 2 is 4, the second derivative evaluated at 2 is negative 7, the third derivative evaluated at 2 is 8. Write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 2.3. So we can create our third degree Taylor polynomial We know the first two terms are simply just going to come from our tangent line, creating our tangent line, which is just y equals y sub 1 plus m times x minus x sub 1. So our y-intercept is going to be 6. Our slope, or our first derivative value at 2 is 4. And then x minus 2. Now it says x equals 2. This is actually the center. So our c value is 2. And then our x value is going to be this approximation that we're after. Okay, so that's the first two terms. Now we can go into the pattern. And the pattern for the Taylor polynomial is now going to be the second derivative evaluated at 2, which is negative 7, over 2 factorial times x minus c, our c value is 2, to the 2 second power. So we know these two numbers are always going to match. And this is the second derivative evaluated at the center. And now the third derivative evaluated at the center is 8 over 3 factorial. X minus c, our c value again is 2, raised to the third power. Now this is our third degree Taylor polynomial. So now we're going to use this to approximate f of 2.3. We know it's not going to be the exact value, but we're going to just use this. We have an approximation polynomial, so we're going to use that to approximate 2.3. So all we do is replace all the x values we see with 2.3. So 6 plus 4 times 2.3 minus 2. 2.3 replaces x. 2.3 replaces x. And we plug all this in our calculator. Or we can simplify this first. All this becomes 0.3, 0.3, 0.3. And f of 2.3 is simply going to be 6.921. Okay, moving on to the next section. The fourth derivative satisfies the inequality. The fourth derivative of x is less than or equal to 9. So we can already see that this is going to be a safe upper bound. This 9 is going to be a safe upper bound that we can eventually use for the Lagrange error bound. For all the x in the closed interval from 2 to 2.3, use Lagrange error bound on the approximation of f of 2.3 found in part A to find an interval such that f of 2.3 sits between a and b. Give 3 decimal places. Now, again, we're dealing with the third degree Taylor polynomial, so we're also going to match that with the remainder. We know this is going to be the remainder for this third degree Taylor polynomial, so it'll be our n value will remain at 3. So again, we're going to be using this formula here. N is 3. Our x value is what we're trying to approximate, 2.3. Okay. Now, because this is our n value of 3, we know that with Lagrange error bound, we're always dealing with the first unused term. So if this is 3, we know all these values will be pushed to n plus 1, or in this case 4. So the fourth derivative evaluated as z over 4 factorial times x minus c, 2.3 being the x, the c value being the 2, and then the n plus 1 is 4. So let's go back to figuring this out. Right now, reading from what we have from part B, we know that the safe upper bound for any value within this fourth derivative has to be less than or equal to 9. So it doesn't matter what the z value is. We know the safe upper bound will be 9, so we're going to replace this with 9 as the max value. So we know that the error cannot be any greater than this expression. It has to sit safely below this value. So we plug this in the calculator, we get 0.00303. We know this is the error. We know this is how much our polynomial is off by. So our polynomial approximation is 6.921. So we know that our approximation will either be off by 0.00303 to the left, or it'll be off by 0.00303 to the right. So we just take the approximation and we just subtract the error on the left side, and we add the error to the right side. And then we know that now we can safely say f of 2.3 has to sit somewhere between 6.917 and 6.924, which is going to be a fairly small error. Okay, so based on this information that we found, could f of 2.3 equal to 6.992? Well, let's compare with our bound here. 6.992 sits outside of our range. So we know we can say 6.992 is outside the interval, so therefore it cannot be equal to f of 2.3. Okay, let's look at this next example, and this is from 2011 BC exam. Let f of x equals sine of x squared plus cosine of x. Our graph, the absolute value of f, the fifth derivative of x, is shown here. Write the first four non-zero terms of the Taylor series for sine of x, and write the first four terms of sine of x squared. So we're gonna, so these a and b will help build this polynomial that we're eventually going to use. So sine of x, we know we should have memorized this: x minus x cubed over 3 factorial, x5 over factorial minus x7 over 7 factorial. Now we want to use this to build the sine of x squared. Sine of x squared, we can simply, because this is Maclaurin series, we can replace every x we see with x squared. So x becomes x squared cubed becomes x6, x squared to the fifth becomes x10, x squared to the seventh becomes x to the 14. Okay, that takes care of part A. Part B, write the first four non-zero terms of the Taylor series for cosine of x, also Maclaurin series. We should have memorized this as well. 1 minus x squared over 2 factorial, x fourth over 4 factorial, x6 over 6 factorial. Now, f of x is a combination of sine of x squared and cosine of x. Well, we found sine of x squared, which are these four terms. We found cosine of x, which are these four terms. So we're just going to combine these terms together to create our polynomial, our function here. Now we're going to use this function to evaluate. We're going to use this function here eventually, but right now I'm going to clean this up as much as possible. So the x squared terms I'm going to combine together. X fourth sits alone. The x is 6 over 3 factorial is 6, and the 6 factorial is 720. So if I combine these to be one term, it'll give me negative 120 over 720. And then this is 1 over 720, which is negative 121 over 6 factorial. So now this is my 6th degree polynomial that I'm going to be working with. Part C, find the value of the 6th derivative evaluated at 0. Now, if we look at this, the 6th derivative evaluated at 0 is coming from this term here, because we know that this must be equal to this expression here. Remember, we're dealing with the Maclaurin series. So we know that f of 6, the 6th derivative of evaluated at 0 over 6 factorial x to 6 is equal to this expression. So if we match it up, we know that the negative 121 must be equivalent to this 6th derivative evaluated at 0. So that answers our question for part C. The 6th derivative evaluated at 0 must be negative 121. Okay, so let the 4th degree Taylor polynomial be given here. We know that the graph here is representing the 5th derivative value at x. And we also, it says, use that to show that the 4th degree polynomial evaluated 1/4 minus the actual function over 1/4 is less than 1 over 3,000. Now this is representative of the remainder. Okay, so this is another expression for remainder. Remember, we said the remainder is simply the function minus the polynomial approximation. But there's an absolute value bar here, so it really doesn't matter which order we subtract those in. So we know that we're dealing with the 4th degree Taylor polynomial, so we're going to have to match that with our remainder as well. So that means our remainder n value must be 4, and then we can plug the rest of this information in. If this n is 4, then that means everything inside here will be pushed to n plus 1, which will be 5. So I'm going to fill that in here. We know that we're dealing with the 5th derivative evaluated at z over 5 factorial, x minus c to the 5th. We know that our x value is 1/4, right? That's the x value they give us. Maclaurin series, so our c value must be 0. So 1/4 minus 0. And now the only missing thing is we have to find a safe upper bound for this value. Okay, so this we're going to refer to our graph, because this graph is the 5th derivative evaluated at f of x. So this is the graph here. Now we know that we don't know what the z value is, but we know that our z value has to sit somewhere between our x and our c value. And our x value we know is 1/4. We know our c value is 0. So between 0 and 1/4, let's see if we can find a safe y value. Okay, so between 0, so this is 1, right? So this is 1/4, 1/2, 3/4, and 1. So between 0 and 1/4, we see that the highest y value is going to be this, whatever this value is. We don't know what this value is. It could be 3, it could be 35, it could be 36. But let's just find a safe upper value, which is 40, right? It's 40, we know it's going to be a safe upper value, it'd be a nice, easy value for us to use. So our safe upper bound, we know this cannot exceed 40, and it's a nice number that we can use. So now we know that our error, or remainder, cannot be any greater than this expression. So 40 over 5 factorial is 120. 120 is 5 factorial. 1/4 to the 5th power is 1024. So if we clean this up, we're going to get 1 over 3072. And 1 over 3072, we can safely say is less than 1 over 3000, which is what they're asking us to show and prove.